We are going to discuss about earthing and its type and importance of doing earthing and which type of earthing is used in which kind of places and advantages and limitations of those earthing types. We are going to discuss also about earth fault loop impedance, fault current with respect to these earthing types, and we will see the comparison of different type of MCBs used with respect to this type of earthing mechanisms, how it trips and everything. Okay, so that's the agenda for this particular video. Let us start with the topic, what is earthing? So earthing is nothing but connecting all the metallic bodies of an installation to the earth or a ground with very less resistance conductor. Okay, so what it means? So if you take an installation in your home, we have many loads like AC, water heaters, socket outlets, lighting circuits, so on. All these loads, the metallic body of these loads or a cover of these loads are interconnected with a conductor which has very less resistance, and it is going to be connected to the ground or earth. Why we need to do this? In case when the human comes in contact with the line conductor where the current is flowing, the line to earth fault happens, or the line conductor directly touches the earth conductor or the earth itself. Let us take an example. A human comes in contact with the line conductor and is being grounded to the earth. How much resistance he offers to this fault current? Obviously, when he is touching the line conductor, the current is going to flow through his body and it is going to be grounded if he is not having proper safety shoes or something like that. So during this process, how much resistance is being offered to this fault current by our human body? A simple data is given here. You can see there are some values given here. And to hand, dry condition, wet condition, how much resistance is there, and to feet in wet condition, how much resistance is there, and maximum and minimum limits is shown here. As a average, we have 4 kilo ohms or near to 5 kilo ohms hand to hand resistance in dry condition, and hand to feet we have almost 1.2 kilo ohms. Okay, let us round it in the kilo ohms. So whenever there is a fault happens, line to earth fault happens through a human body, so the fault current needs to flow through this value of resistance, which is having the value in terms of kilo ohms. Suppose if we can able to provide a less resistance path for this leakage current, for example in terms of 2 ohms or 3 ohms, so the current always prefers the least resistance path. So if we can able to provide a less resistance path for this fault current, then so the fault current prefers to flow in the less resistance path. Though the leakage happens from the line conductor to the body of the machine or the wall or whatever it is, when the human comes in contact with that machine, the fault current doesn't prefer the human body which has the resistance in terms of kilo ohms. Instead, it prefers the path which has less resistance through the earth conductor. So this is the idea of providing the less resistance path for fault current. So, this process is called as earthing. So, this is a simple intro for the earthing. So, why we do? Obviously, it is for a human protection. Any fault, any leakage current happens in our installation must be grounded to the earth, not to the human body. So, this is the purpose. So, what are the different type of earthing used all over the globe? We have TN, TT, IT. What is this TN? So, TN meaning that how the earth conductor and neutral conductor is placed in the supply system. We get the energy from the supplier and we consume it in the consumer part. So, how this neutral and earth conductors are provided by the supplier, based on that we have the classification. So, we have TN, TT, IT. So, in TN we have TNS, TNC, TNCS. What is the meaning of this each individual letter? So, T refers earth. So, it is the word from French terre. Terre means earth in French language. So, T denotes earth, N denotes neutral, S denotes separate, C denotes combined, I denotes isolated. Okay. So, let us get into the details of the earthing types. So, first let us discuss TNS. TNS, if you see the picture at the right of your window, you can see I have a distribution transformer in this picture and I have a distribution board in my home, that is in my consumer site. From the supplier, how the line conductor, neutral conductor and earth conductor connected from the supplier to the consumer is shown here. I have taken a single phase supply to the consumer. So, I have a line 1 which is having a red color 1, and we have a neutral which is denoted with the black color, and we have a earth which is denoted with the green color. Okay. So, you can see in this picture the line and is connected here, and the neutral is connected from the supplier to the consumer in a separate conductor, and earth also has a separate conductor from the supplier to consumer. So, that is why we call this as a TNS. So, TNS meaning, so earth and neutral having separate conductor from the supplier to the consumer. Okay. So, this is how it is being connected. So, let us discuss more details about it little later. So, let us see the other earthing methods as well. So, we will see TNC. So, TNC, if you see this picture, you can see that the neutral and earth is combined together in a single conductor from the consumer to the supplier. Okay, so, we have only one conductor. So, it serves two purposes. It acts as a neutral as well as it acts as a earth. It is combined. Okay, protective earth and neutral together. So, let us go to the next type where we have TNCS. So, here from the consumer supplier side, the neutral and earth is combined in a single conductor. It comes until the installation of the consumer. Okay, so, until the distribution of the distribution box of the consumer, it is only a single conductor. From that distribution box, it is being split into two conductors, one for neutral and one for earth. So, now we have two conductors in the installation and single conductor from the supplier to the installation entry point. So, this is TNCS method. And then TT. Here you can see we have only line conductor and neutral conductor, and there is no earth conductor in any means, and the earth conductor of the installation is connected to the ground there itself, and the consumer has its own, consumer having their own earthing, and they are doing the earthing in their own side. There is no conductor connecting this consumer earthing and the supplier earthing. Okay, so this is TT, and we have as well as IT we have. So where we have the consumer, the supplier side, the earthing, either the earthing will not be done or it will be done with a high resistance or high inductance type of earthing. Okay, so this isolated means, so in the source side or the supplier side there will not be earthing, or even if it is provided, it will be provided with a high resistance earthing. In the consumer side they have the earthing. Okay, so in the consumer side we have the earthing. So in the supplier side it is isolated, and in the consumer side we have a earthing. Okay, so these are the different type of earthings. So let us get into the details how this earthing method is going to differ with respect to the fault and with respect to the earth fault loop impedance, and how it is going to differ with respect to the MCB's tripping time. Okay, so now we will go to the TNS method here. So we have a TNS method here. So whenever there is a fault happens between the line and earth, so the path which is followed by this fault current is given here, as I shown here in this picture. In the right side picture you can see when there is a fault happens, you can see there is a fault, the leakage fault happens here. So when there is a leakage fault happens in this TNS method, TNS earthing system, what happens, the fault current is flowing from the source in the line conductor, and it starts flows in the earth conductor, and it goes back to the source. Okay, so usually, so this path for the fault current provides certain resistance. So this resistance is called as earth fault loop impedance. Okay, earth fault loop impedance. Earth fault loop impedance. So this impedance for our TNS method ZS, they denote it as a ZS. Okay, so for the TNS method you can see the resistance of the line conductor and the resistance of the earth conductor. So we can say R1 of R1, which denotes the resistance of the line conductor, and R2, which is the resistance of the earth conductor. Usually this resistance for this TNS method, usually it ranges up to 0.8 ohms. This is a normal value. Okay, 0.8 ohms. Right. So let us consider we have a MCB or we have a fuse. Let us consider I have a MCB for this faulty situation or faulty circuit. Let me take a B10 type MCB. So what is B? Is a type. So for the MCB we have B type, C type, D type commonly used. So B denotes the type and C10 denotes the IN value. So IN means normal operating current and B denotes the type of MCB. Okay, for B type, the trip range for the B type is given with the formula 3IN. So that is a 3 times of normal operating current to 5 times of the normal operating current. If you substitute the value for IN here, we get 30 ampere to 50 amperes. Okay, so this is the trip range for this B10 type of MCB. When the fault current reaches to 50 amperes, the B10 type MCB is going to trip instantaneously. That means immediately it is going to trip without any delay. Suppose if the fault current is lesser than 50 amperes, 40, 30, 20, it will trip, but it will take its time. Okay. So, when it reaches 50 or above, the B10 type of MCB is going to trip very fast. Okay. It is going to trip instantaneously. Okay. So, let us take one more type of MCB. So, let us take D32. D32. For D type, the trip range is given, the formula is given 10 IN to 20 IN. So, this is the formula. So, if you substitute the value for this, so we get 320 amperes to 640 amperes. So, this is my fault trip range. So, the instantaneous trip current for this D32 type MCB is 640. Okay, let us keep this aside and let us see how much fault current flows during the line to earth fault in this TNS earthing. I fault current, you can say IPF, the prospective short circuit current, IPF, or I, just I denote as I. Okay. I is equals to 240 volt. I have taken a single phase supply. So, 240 volt divided by my loop impedance is 0.8 ohms. So, the value is 300 amperes. 300 amperes. So, this is the fault current, prospective fault current, which could flow in this TNS earthing system. So, 300 amperes of current can pass through this, right. So, if I have used the B type of MCB, okay, so B10 or B20, even you take B20, so you will have 60 to 100 amperes. Okay, so if it is B20, so you will have 60 amperes to 100 amperes. Okay, so various, so this is for B20. Now, if you see the instantaneous current which is required to trip the MCB is 50 for B10, for 100 for B20. And what is the fault current which is flowing during the fault in the TNS system is 300 amperes. So, that means when we are using B type of MCB with a TNS earthing system, 100% it is going to open the circuit without any problem. But if you see this D type, that instantaneous trip current which is required is a 640 and I have only 300 amperes of current during fault. So, this means the D type MCB, if I use in the TNS earthing system, it is not going to protect us and it is not going to trip during the faulty condition. Okay. So, this is a simple comparison. Okay. So, this is a simple comparison between B type and D type MCB which is used in TNS earthing system. So, let us move on to the other type of earthing system. So, let us go to the TNCS. So, where the TNCS, let me take the same example here. So, I will just copy this. I will just copy this data. I don't want to write it again. Okay. So, for the TNCS, so B type and D type, I have taken the same example, no difference in that. Let us calculate the short circuit current. I equals to 240 divided by, here for the TNCS we have usually 0.35 ohms of resistance. Okay, so this is the loop impedance. So when we calculate the current for this, we get around 685.7 amperes. Okay. So for the TNCS method, the fault current during the earth to line to earth is 685.7 amperes. If you are using B type, we need only 50 amperes for tripping if it is a B10. If it is a B20, it is 100 amperes. But how much fault current do we have? It is 685.7 amperes. So that means B type is going to trip without any issue. And D type, let us consider the D type MCB. If we are using a D type MCB with the TNCS earthing mechanism, you have still the trip current is 640, the maximum instantaneous tripping current is 640, and I have, how much is the fault current I have? 685. So that means even the D type MCB is going to trip. The D type MCB is also going to trip, and it is not also going to have any issue. You can compare these two earthing mechanism for the same MCB. I have taken the same MCB B10 and B32, and I have calculated the current, that is a fault current, and I am comparing these two. Okay, so if we are using a TNCS earthing mechanism and the same MCB can trip for the same for the fault, but D type which we have used in TNS couldn't able to trip. Okay, so this is the simple comparison again. So let us go to the another one. So TT. So here for the TT, this is the loop. For the TT, I have shown here, this is the loop for the fault current. So the current is going to start from here in the line, and it is going to follow here, and then it is gone to the earth here, and then you see here there is no conductor connecting between this earthing in the consumer side to the supplier side. So how this is closed, the loop is closed, it is through the earth or a ground. Okay, so that means the external resistance, not only the conductor resistance, the earth resistance, that is external ground resistance also comes into picture for a TT earthing. So this is at E, the resistance of the ground or the resistance of the earth is denoted as ZE. So in the TNS or TNCS, ZS equals to only R1 plus R2, that is line conductor resistance and the earth conductor resistance. But here for the TT, it is 3 variables coming into picture, R1 plus R2 plus ZE. So ZE is the additional parameter. So ZE is the resistance of the earth or a soil here. So it depends upon the soil resistance, the ZS, the loop impedance will change. If the loop impedance is very high, then obviously the fault current is going to be small. Okay, so here let me take, so usually for the TT mechanism, usual ZS value is range from 21 ohms to 100 ohms. So this is the normal range for the ZS value for TT mechanism. Suppose if you get more than 100 ohms, so that means you need to check your earth resistance and you need to take a preventive measure so that the earth resistance can be reduced. So go back to the same calculation, we will go back to the same calculation. Let us see how much fault current flows through this TT mechanism during the line to earth fault. So, I equals to, let me consider both case, the best case as well as the worst case. So, let me take I equals to 240 divided by 21. So, it gives around 11.42 amperes. This is my best case fault current, and for the worst case fault current I get 240 divided by 100. So, if you consider this, you get 2.4 amperes. So, this is my fault current for TT earthing. So, we have seen for B type, suppose if you have a B10 MCB which is connected in TT. See, my normal operating current itself 10 amperes, the normal operating current. So, B10 usually will be connected to the lighting circuits. Okay, so, if you have AC or water heater, still you will be having a more current ratings. Suppose if you have a AC, you will have 32 or 20 amperes like that MCBs, and if you are having a socket outlets, you will be having 20 amperes current rating for the MCBs. So, if I consider B10, the smallest size of my MCB B10 itself couldn't open, because the normal operating current itself 10 ampere, my fault current which is flowing during the leakage fault is only 2.4 amperes. At the best case I get only 11.42 amperes. So, this earthing, TT earthing method, if you are relying on the MCB for opening the circuit during the fault, it is not going to happen. Okay, it is not going to happen. So, the reason you understood. So, because of the loop impedance is high, because of this loop impedance is high value, what happens? The fault current is very less. So, because of the fault current less, you cannot have the MCB opening during the line to earth fault. So, what can I do? How I will protect myself? So, you can have a device called RCD, residual current device. So, this device has the principle of working not like a MCB, it is having a different principle. So, it is going to compare the line and the neutral current always, the line and neutral current always. So, if the difference between this line and neutral current exceeds 30, or I can say I delta n value. If it exceeds I delta n value, usually the I delta n value will be 30 or 100 milliamperes. If it exceeds this I delta n value, the difference between the line and neutral current exceeds the I delta n value, which is 30 or 100 milliamperes. So, immediately the RCD will trip. So, in case of TT earthing, RCD is very essential, it is must. Okay. So, this TT is having its own advantage, TNS is having its own advantage. Okay. So, there are some advantage for TT, there are some advantage for TNS, there are some advantage for TNCS. So, according to the requirement, we can choose the earthing mechanism. So, this is a simple comparison for the same type of MCBs and same rating of the MCBs, how the fault current differs and how the tripping time differs for these three different type of earthing mechanisms we have seen. So, by this you can have a conclusion. So, where I can use a TNS and where I can use a TNC and where I can use a TNCS and where I can use a IT. So, I have quoted here simple comparison for this three different type of earthing, 5 different type of earthing systems. So, earth fault loop impedance is very high, okay, high here in the TT mechanism because of loop impedance. So, we have a ZE here. So, because of the ZE, so we have a high resistance. IT, it is going to be very high because we intentionally open here, there is no earthing here, or we will have a high resistance earthing. Apart from that, there is no conductor connecting here. So, this is also will have ZE resistance also here. So, ZE is there. If it is connected here with a high resistive earthing, or it is open, still in both case it is going to be very high resistance. TNS is going to have low, as we discussed we have only R1 plus R2. So, that is line conductor resistance and earth conductor resistance. This is common for all these three different types, and TNCS is going to have still little lesser value. Okay. So, this is how the earth resistance. So, based on this earth resistance we have discussed what happens with the short circuit current, fault current, and when the fault current goes higher or lower, what happens to the MCB, whether it will trip or not, we have discussed. So, we can have a conclusion over there. So, RCD is preferred for these earthings or not. So, RCD is very much required for TT. So, without RCD, so this earthing system or this particular configuration, earthing configuration is not going to work, and it is not going to give any protection. So, we must have for a human protection here RCD, and for this TNS, TNC and TNCS, it is TNS and TNCS, it is optional. IT is not applicable. So, since we are having only transmission line kind of areas, we use this one. So, we do not use RCD here, and TNC not required. Okay. So, mostly the most commonly used earthing systems are TNS and TNCS and TT. So, these are the three different type of earthing system in commercial and domestic area you can see. And then, so mostly even in the TNS nowadays in our buildings you can see even TNS or TNCS, they provide a additional protection by using a RCD. Okay. So, even if you not connect a RCD here, it is not going to harm you, but it is always preferred to have a RCD, so that even the earth conductor resistance is increased, or the old buildings the resistance is more, or leakage it is not detectable. So, even in that case the RCD can help you, and it can trip during the earth to line to earth fault. Okay. So, protective conductor cost, if you see the conductor cost, obviously TNS is going to have highest cost, because we have a separate line conductor and then separate neutral conductor and separate earth conductor. So, we have from the supplier to the consumer we have 3 wires. Okay. So, obviously the conductor cost is going to be highest in the TNS, and then TNCS is high. Why? Because it is coming until the installation. From the installation it is gets split into earth and neutral. So, again the cost will be high, but highest is TNS, and TNC even inside the installation it is going to be combined, only neutral and line conductor is going to be there. So, it will be very less. And then TT, so inside your installation you are going to have earth conductor and neutral conductor separately, and it is going to be connected to the earth. So, inside your installation you are going to have the earth conductor, and inside even in the distribution side they are going to have the earth conductor. So, here the cost will be low. So, very less one is a TNC, and the other one TT is low, highest one is TNS. Okay. So, safety wise, this is the important parameter. Safety wise, the safest one is the TNS, because the supplier is going to do the earthing, and they are going to maintain the earth pit and all those things. So, the earth resistance is going to be maintained very less. So, in case of any fault, so obviously it is going to trip fast. So, the safest one is a TNS. And TT, if you have a proper earth pit resistance and everything, if it is maintained properly, it is safe. The less safe one is IT, and TNCS is also safe, and TNC is least safe. That is why they are not using this one, because the neutral and earth is combined together. So, sometimes the RCD cannot differentiate, RCD cannot differentiate the fault current. So, because of that it is not preferable in most of the places, least safe. And Safety risk, if you add, this is what I was telling. So the loop impedance is very high in case of TT, and it is very high for the IT. And safety risk as concerned, if you say take the TNS, if the broken neutral cannot be found, and the same thing for all these three different type of earthings. So advantages, if you compare advantage, safe and reliable for the TT. The cost wise, TNS is very costlier one, but it is safest one. And here TNC cost wise very less, but safety wise it is not good, so we don't use this one. TNCS provides a mix of safety as well as cost. Some places they use the TNCS as well. Okay, so where I can use which type of earthings? So you can see here TT, TNC, TNS, all those things is given here. TT is used overhead power distribution for residential, commercial, for a common transformer. Every installation shall have an RCD and earth electrode at origin of installation. So TNS, industrial, commercial, IT buildings with electronic systems and transformers in facility. TNC, overhead power distribution up to origin of an installation. TNCS, overhead power distribution for residential, commercial, for a common transformers. So IT, hospitals, IT installations for a building of part of a building. So not suitable for different building with the same supply. So these are the place where I can use the different type of earthing mechanisms. So this is a simple understanding what I have with the TNS and other type of earthing mechanism. So as much as possible I have explained it. Hope it is clear. If you have any doubts, please let me know in the comment box. Thank you so much. Let us meet in another video with another good topic.